I'm going to discuss the concept of sampling distributions. It's kind of a difficult thing to wrap your head around, but once you get it, it's pretty easy to use. What we're going to look at is a situation that is a normally distributed variable here. In this case, I'm looking at heights of adult females all around the world, 64.5 inches, so about 5'4.5". And standard deviation at 2.5 inches. Basically, what I have here is we're saying the percentage or probability above 5 feet tall or 60 inches. That's 96% of female adults. So you could use male average height and standard deviation. You could do a whole number of things with the normal curve. I just wanted to do one that would be a little more familiar with you so you can kind of understand what's happening here. I always like to click this button, then we can see where each standard deviation is. So 6 feet tall, for example, that's 72 inches. That's going to be unusually tall. And then 57 inches would be 4 foot 9. That would be kind of on that lower end, and we have most heights kind of in between there. So with sampling distributions, what we're doing is we're theorizing what it would look like if we took samples from this distribution and kind of wrote down the average of each, and then looked at that as a distribution. So here's kind of what it looks like. I have that same population here. Let's say we're taking samples of size 10, and I'm going to start with just doing it one at a time. So there's 10 female adult heights. We can see that, it's kind of random, but it is coming from this distribution. So the average, 64.4, is actually pretty close to the average there. All right, so then I take another sample, and each time we take the sample mean and then we plot that. So we're sort of collecting all of them in the far right here, and we're just going to plot those, and that's happening one at a time. Let me bump it up to 100 at a time. So 100 samples. This is just going to show the most recent sample. We added 100 more over here. These are all sample means. And if I continue on long enough, you get kind of a robust data set that actually follows a bell curve. So what's going on here is we are averaging 10 heights, and that's going to give you a number somewhat close to the population mean. If we do that over and over and over again, most sample means will be very close to the population mean, and some oddball samples will be farther away. So you can see maybe being up here means you had an unusually high sample mean. Down here is unusually low. That whole idea of kind of grouping up towards the middle, that is the normal distribution. So we started with a normal distribution. After we took enough samples, we ended with one. Now what you can do, and if you want to go to this website, this is rossmanchance.com. There's a whole bunch of applets here that are pretty cool. I'm going to go to a finite population. All right, so this is also a bell curve. I'm going to pick one that's maybe not a bell curve. In this one, this is a uniform distribution, or just we could say it's not a normal distribution. It'd be similar to, maybe rolling a 6-sided die, although it looks like we have a lot more outcomes than 6 here. And we're going to sample from that population. So let's start with just one at a time again. You can see that these are all going to be pretty uniformly spread out. Sometimes you don't even have any repeats at all. All right, so I'll go and bump that up to a big number. Let's just go 1,000. Let's take 1,000 samples real quick. Now this time we also have what looks kind of like a bell-shaped distribution. Same thing's going to happen. If you take an average of this uniform distribution, your sample may be still pretty uniform, but what you're finding is the middle of it. Then you're plotting that over here. So the middle of each sample will tend to be close to the middle, and be far from the middle less and less often. So if we had a sample mean of, say, 0.8, for example, that would be way over here. It's unlikely that we would get a sample mean that high, but it can happen periodically. So this is a concept of sampling distributions. What you get is, and I'm going to go down to the central limit theorem, you're taking samples, you're finding the sample mean, and no matter what shape you start with, the sampling distribution, which is that one that we created on the right, will tend towards a normal distribution. To be precise, if you start with a normal curve, you're going to end with a normal curve, no matter what. That's what happened when we looked at heights. If you don't start with a normal distribution, you're going to want to shoot for a sample size of at least 30 to really make sure you get that bell shape. So we kind of have the bell shape. It does have sort of a weird spot in the sides, and I don't think that's just an accident. We would really want to go up to samples of 30 here, and then we could get a nice bell curve without any features that make it steeper in one area than the other. It's going to have that smooth kind of curve throughout. And then we can predict what that bell curve would look like. The mean of the sampling distribution, so this is the mean of all those sample means, is the same as the population mean if you collect enough samples. And then the standard deviation of this new distribution we created, over here it's called standard error. And that will be equal to the original standard deviation divided by square root of n. So as n gets bigger, you're bunching things up closer and closer to the middle. Here's a little more interactive look at that. So that's our same bell curve. I'm going to put in this divided by square root of n and use a slider there. So if we started at 1, that would be like looking at individual heights. And again, we're just looking at height of human females, because male and female have different averages and standard deviations. So we have that 64.5 mean, standard deviation of 2.5. So these would be this would be the distribution for individual heights. Again, earlier I did what percent are below or are above 60, about 96%. That's just an example that we could look at there. Now let's say we take samples of 10. So you can even see right away it's already grouping towards the middle. So now we're looking at a distribution of sample means when we take 10 at a time. So if we wanted to talk about probability, it would be worded a little different. If we wanted to find, say, the probability of a sample of 10 where the average height is above 5 feet, then we would plug 60 in here. That's going to be a lot more likely. And you can rescale this and it looks exactly like where we started. But it's important to note we started with a flatter curve. So there's the flatter curve or lower curve, and it's going to get sharper and steeper as n increases. And I'm going to set n way up to 150. You can see there's not a lot of variation. Imagine if you took a sample of 150 and average the heights. It's going to be a pretty reliable measurement. You're not going to have extremes there. So you're going to really be close to the population mean more often. To do this in StatCrunch, you do have to do a little bit of extra work on paper. So I'm going to use the scientific calculator here to show you those steps. Here's StatCrunch. This was the original distribution. Now what I'm going to do is just change the standard deviation. So if I have a sample of 10, then I need to take 2.5 divided by the square root of 10. And now this will be the standard deviation of the sampling distribution. So I'll round it to 4 decimal points, 0.7906. So this is an average of 10 with a height above 60 inches. That's very likely. And you can see this automatically rescales it. So we don't see it getting narrower, but we just have to notice that our standard deviation is getting narrower. Let's say I had a sample of 49. So 49 is a nice square root of 7. That's 0.3571. Then I'll just go back over to StatCrunch. 0.3571. Shrink that standard deviation down more. And now I'm looking at a sampling distribution of a sample mean with samples of 49. So it's pretty easy to use for the sampling distributions of the sample mean. It's kind of a lot to say. We usually just say, the sampling distribution of X bar. We would say mean of sample mean, standard error. And we can do the same thing with sample proportions. There are a couple of requirements here. NP times 1 minus P has to be greater than or equal to 10. The mean of sample proportions is the same as the population proportion, and that would be our standard error.